Good afternoon, dear participants of the conference. Today, the authors from State University of Information and Communication Technologies and Kharkiv National University of Radio Electronics present a paper called A Method for Mathematical Modeling of Traffic Distribution in Multi-Link Devices. The introduction of multi-link operation (MLO) in the IEEE standard expands the frequency resource by aggregating several independent links, which enables the use of traffic distribution policies across available interfaces. Different policies already implemented by equipment manufacturers and in research projects produce divergent latency and throw output results under identical operating conditions. This gives rise to a scientific and practical problem: justified selection and adaptation of a traffic distribution policy for given network conditions. Currently, there is no unified model that describes policies in terms of standardized metrics, decision-making rules, and resulting performance indicators. Among the studies on traffic distribution method in IEEE networks, the following approaches can be distinguished: machine learning adaptive algorithms, parallel transfer learning, recurrent dynamic traffic distribution, binding traffic identifiers (TIDs) to links, dynamic balancing to the least loaded links, sending a packet to the first available link. Therefore, given the large variety of proposed MLO traffic distribution algorithms, it is necessary to develop a model capable of describing any policy in standardized terms of its input data, decision-making rules, and resulting metrics. The aim of this work is to construct a unified mathematical model of traffic distribution in an MLD, which formalizes the data transmission control process at the upper MAC UMAC level as a decision-making problem in a queuing system, thereby creating a foundation for comparing different control policies. In the context of this work, MLD is considered as a querying system with controlled packet distribution among several links operating in a stochastic environment. Control of this distribution is carried out of the UMAC level as the sole decision-making point, while each link has its own access procedures and its own process for assessing the medium to obtain transmission opportunities. To decide where and how much to transmit, the scheduler collects information about the current situation using the equation at the screen. For each link, it obtains four metrics: channel occupancy level, interference level, signal quality, presence of a hardware conflict with another link. And for each query, it tracks amount of buffered data and remaining time before the permissible delay is violated, using the equation number 2. Based on this data, the scheduler generates a control action consisting of three components: assignment of flows to links, it is binary metrics; volume of data to be transmitted, this is load distribution matrix; transmission during per link, TXOP vector. To evaluate the quality of chosen plan, the method calculates three performance indicators directly from the control action and the current system state: expected throw output for each flow, average packet delay, including queuing time, channel access waiting time, and transmission time, probability of missing the deadline, the risk that data will not be delivered within the permissible latency bound. By average these indicators over all flows and over many scheduling cycles, it becomes possible to quantitatively compare different traffic distribution strategies under identical conditions without running tests on real hardware. Not every desired transmission plan is physically feasible. The method accounts for three key constraints derived from actual hardware operation. Some link pairs interfere with each other. If both are active, their TXO durations must be equal. If several links are served by a single radio module, transmission is possible only for one of them at a time. So, AMDPU aggregation limit, a single frame cannot combine an unlimited number of different TIs. In addition, the method considers protocol overhead and the necessity to align TXO durations to the slowest link within an NSTR group. The simulation results that show that the effectiveness of traffic distribution policies is determined not by the number of links, but by the alignment between the load, the link's characteristics, and the state of the environment. The application of our methodology demonstrates this mechanism. By integrating the physical parameters of the links, in this case asymmetry, into the delay formulas, we found that adding an additional but slower link creates a bottleneck effect. Instead of expected increase in throughput, the total QL length increases due to the reliability slow link, causing the overall MLO performance to drop to the level that would be achieved by transmitting only through the single fastest channel. So, the proposed methodology allows for an informed choice of traffic distribution policies by pre-assessing their consequences. The method's ability to calculate the probability of failure based on exponential service time distribution provides users with numerical thresholds for switching distribution policy. In other words, implementing this method can enable the testing and configuration of UMAC level schedulers for MLO devices. Thank you for your attention.